So we're going to be doing a presentation on developing standards to assess the resilience of batteries to abuse. I'm John Lesage. I'm with Automotive Digest. I'm Automotive Editor of Green Initiatives, and we cover fleets and OEMs and suppliers, dealers, and I'm going to say a few things about some of the panelists you'll be hearing. First of all, Keith Wilson, Manager, Technical Projects, Ground Vehicle Standards, SAE International. He oversees projects and standards activities related to advanced vehicle technologies and is involved in developing innovative business strategies surrounding safety systems, electromobility, chassis, materials, processes. And we've also got Keith Konecki from Fisker Automotive. He's Engineering Manager, Energy Storage and Power Conservation. Let's see, he and his group are responsible for energy storage and high voltage components on all the Fisker programs, including energy storage system, charging system, and high power inverters. Galen Ressler, GM Technical Fellow at GM Company, has over 25 years of vehicle safety experience, including crashworthiness, electronic sensing, advanced active safety systems, and most recently, battery system safety. And Eric Speck, Chief Engineer, TÜV SÜD Canada, Chief Engineer with technical responsibility for battery verification services in North America. So thanks for being here, and for all of you. We're going to go and talk about some of these issues here for about an hour, and then we're going to have an opportunity after that to engage in dialogue and questions and conversation. So thank you guys for being here. And what we'll do is we were able to identify topics based on kind of what's going on in the auto industry and in battery design technology. And the first one we were talking about, and we did a conference call recently, was right now we have a number of years, 12 years or more of where nickel metal hydride batteries are common in hybrid electric vehicles. And they're in their latest version now, still out there. So one of the things would be is we have some experience with lithium-ion batteries, which is still pretty new. How does this compare? How do these technologies compare? How are they different? Lessons learned? And we thought Eric would be good to speak to that first.
Okay, John, thank you. It's probably worth looking backwards a little bit, in fact, a long time, to the start of the development of nickel batteries, not particularly nickel metal hydride, but the nickel electrode itself, which is extremely robust. It started off in about 100 years ago in development, plus or minus a decade or two. And it's probably pretty lucky that we started HEVs with that technology. The application using that rather robust technology wasn't the toughest in the world either. Some will argue that it requires a lot of power to give the acceleration you want from a very small pack, but nevertheless they've survived very well. Great warranty record with very few exceptions. So it was the bright star to start off the whole industry with. And then in contrast, if you look at lithium-ion, much less time in development, probably only about 25 years or so, in a serious way. And then we've got something which is much more sensitive than nickel ever was. It doesn't have the benefits of that nickel side of the electrodes. We've got a built-in fire triangle with a lithium-ion cell that we're trying to overcome very quickly. So it's not surprising that perhaps the public sees that where HEVs were really a non-event from a challenge point of view, at least in their eyes, now lithium-ion has issues that need to be solved. It's probably hard for them to understand. So if one lesson can be taken from all this, it's perhaps that you can't push this faster than it's going to go. 100 years of nickel development, admittedly with primitive tools over all those years, compared to what we're trying to do now, presents a serious challenge. And part of that serious challenge is the safety aspect. The consumer or the operator of the car typically wants four things, speaking from an overview. They want power for acceleration, and they want energy for range, they want low price, and they want safety. But safety doesn't show up until there's an issue, and it can be a real showstopper. So if anything is a lesson learned here, it's you got to pay attention to that fourth item that everybody's really interested in.
Yeah, and I would like to agree with that and jump on the part about the success story of nickel metal hydride. So I think if we look at the different products out there for the strong hybrids and mild hybrids, the Toyota products, the Hondas, GMs, Fords, they're very successful right now in the marketplace. There aren't any major hits against the products, and a lot of that was because of the strong development process that was done on those programs for that. So the success story is that we have a very good development process as a starting point, with a safer, maybe more benign technology, nickel metal hydride, but now we can bring that and expand upon that in the areas that Eric talked about and need more emphasis as we move into lithium. But we've got a really good, solid starting point to build off of.
I think I can add a little bit to that from our experience at TÜV is that we've done an awful lot of abuse testing. We decided to focus on that from the beginning of our business several years ago, and we've seen trends over the last 2 to 3 years in certain tests that say this industry is grappling with the issue of abuse. Cells are getting better in tests like penetration, overcharge, and in fact one manufacturer has shown evidence that he can couple overcharge with a penetration test and show some dramatic improvements. So that kind of thing is, as a lesson learned, is you probably got to stretch the boundaries to find out where you're going to be at when this product goes to the customer.
I have a question about, you also have a lot of light consumer products that have been using lithium ion for a few years. How do you translate that into a 3,000-pound car?
Good question. I think you can look at this as that, a large battery pack, and I'll apologize for the analogy, but it's almost like a lithium-ion pack is like a kindergarten class with a teacher trying to keep it in control. And a couple of them go out of bounds, and the whole pack is liable to go. So that's the challenge you have with a big pack. You don't have that with a small application, where a few cells can be managed and basically told to do what they're supposed to do. So it's not only the chemistry of the cells, it's not only the cooling of the pack, it's also the management of all those working in conjunction with each other.
I think as well with that issue as as we began the development with lithium ion from a safety perspective, I think the experience and background from the smaller consumer product kinds of testing and what are the test protocols and what are the technologies and so forth, were all, I'll say, initially applied without necessarily a full understanding of what they might mean in the context of a larger system. And I think now as we've had some number of years in the development of these larger systems, we're beginning to identify areas where some of those test conditions maybe can be modified to some degree in order to support the larger battery systems, as well as some that are perfectly fine the way they are, and then as well I think as Eric mentioned, keeping the whole pack working together, not only from a cell perspective, but a lot of ancillary systems. I mean, when you go from a single cell in a cell phone that's very, very small, there's not a lot of system complexity there that you really have to deal with. It's pretty much the cell. And as you get into something that's weighs 100 plus kilograms and a meter or more in length, there's a lot more complexity in those systems, and so that becomes then something that's unique to this application, certainly compared to the smaller consumer applications.
We were also going to be talking about you gentlemen do have some field experience, and we were first looking at the plug-in hybrid electric vehicle systems, which now, especially with the Chevrolet Volt and Fisker Karma, have some experience. Certainly you have your production time, and you have your driver experience and service and so, things like that. What do you, what could you share about that on this topic right now?
Well, I think from our perspective, we think the field experience that we're gaining is absolutely crucial to our continued ability to develop and introduce successful products. There's been a number of things that GM has implemented relative to monitoring vehicles in the field through our OnStar capability. We've actually implemented a system that gives us not only the ability to know about accidents that may occur with a Volt vehicle, but also with the owner's permission, gives us the ability to periodically download data and learn things about normal usage, as well as then be informed about some of the more severe outcomes. It was also helpful during as we were trying to understand the effects of large amounts of floodwater on these kinds of vehicles here last fall after the Sandy came up the East Coast. There was opportunity to use that system as well to provide some insights as to which vehicles might deserve more investigation. One of the things that we've learned out of it, frankly, is that the vast majority of field events, and most of these are accidents, the vast majority of those things are completely benign as it relates to the battery. Sometimes things look very severe from a vehicle perspective that end up having no effect on the battery at all. And through our investigation, and basically there's a process that we go through that begins with notification of an accident, some data evaluation that's done, decisions are made about whether an on-site inspection is necessary. If it's necessary, then we'll send engineers out to do that investigation, and then based on what the results of that investigation are, then there will be further follow-up that's done, and actually a decision made as to whether or not there's a need to take further action in order to assure safety. And the good news is that in nearly all of those cases, there has been no further action necessary. The other part that comes in with this field experience issue is making sure that when something does happen, and I'm sure you're all familiar with and it's not really a field event, it's more of a external laboratory event, the incident that occurred with the Volt following the NHTSA crash test. One of the things that is critically important is an analysis to make sure that we really understood what happened. There's no shortage of people in the press who are more than willing to speculate and provide their opinion as to what occurred before even the first engineer has taken a look at what had happened. And so it's really important not to focus on what the presumption is or even what maybe some of the initial theories are, but to actually conduct a very methodical, thorough root cause analysis to really understand what has occurred, because it's only when we understand what really happens that we can then take steps in the future to address something that might need to be addressed, to begin to initiate standards if it's something that we think is relevant to multiple kinds of applications. And it's really important to go through that process. I mean, even right now, we're sort of watching real time with the 787 incident. There's things reported in the public, and there's words, and I do it too, and I'm sure all of you do as well, of begin to try to interpret what words are spoken by the NTSB or what the photographs look like they show, to try to sort that out. But it's really important that we all do our best to withhold that judgment until those who are close to that, who are expert in that area and who are responsible for that investigation, can actually go through that process and truly identify the root cause. And then once we know that, then I think it's appropriate to begin from there. So that's kind of our view on this issue of field experience and how we might be able to apply that back into even standard setting.
Thanks.
Yeah. At Fisker, our field experience has been invaluable. So being a small company, and some of our early customers are also our investors. Excuse me. So they often have a direct line of communication to our executive team, so we get some very direct feedback from our customers firsthand with what they like and what they don't like. Then it goes, of course, to the engineering teams to work on anything they don't like. But two examples to build off of what Galen already said. On one end of the spectrum, we found a big focus is on the E-range display. So we've taken that to heart, and we're working on another, some new iterations and new algorithms to better communicate to them what the E-range is, as well as to adapt to their driving style. And also be able to adapt to the different drivers if you alternate between a couple different people driving the same car. So we found that to be something that's a very important customer pleaser feature. On the other end of the spectrum, as we talked about Hurricane Sandy and the lessons learned there. So the standard for submersion test is typically 1 meter submersion for 30 minutes. That's a standard I think a lot of us follow. But as was discussed this morning, the Hurricane Sandy the cars at the port were all under at least 2 meters of water, if not more, and it was for hours that they were submerged for. So that's a situation where it went beyond where our current standards are and where we're currently testing to. But we're looking really hard at the battery packs as we disassemble them to get some lessons learned on what things can we do to make them more robust. Even though that's going to be a destructive event, you don't expect the car to be able to drive away from an event like that. But are there some, as we're taking them apart, are there some simple design changes we can make, some features we can add to make it, not look like the pictures that get broadcast around on Jalopnik and other places.
I was just going to say, I think one of the other keys to thinking about these field events is trying to sort out the extreme catastrophic event that maybe there isn't a need for a standard versus the things where there might actually be something that needs to be done. I think this submersion is a very good example of that. Without question, and there were volts in the same area. Certainly, we didn't get on Jalopnik quite as broadly as some of the other vehicles did, but trying to decide, is there something that happened there? Do we need a 2 meter submersion test? Do we need a 5 meter submersion test? Does it need to be 2 hours instead of 30 minutes? Does it need to be only 15 minutes to reduce the time that it has to get in? Those kind of questions need to be answered, as well as then the question of, well, the vehicle's not gonna drive away anyway. My understanding of root cause around that was perhaps it wasn't related to high voltage battery system at all anyway. And maybe everything that happened is in fact things that you would kind of expect to happen if you take an electrical device and submerge it in salt water for an extended period of time, in which case there really isn't a need for it. So we have to sort out what's the stuff that we need to address compared to what are the things that maybe we don't necessarily need to address, because not every field event, not every quote incident that occurs necessarily needs to result in some new standard, whether it's an industry standard or whether it's an individual manufacturer standard.
I have a question for you about the process of recall. It seems like it's gotten a lot smoother and more direct and prompt these days than 15 years ago. If there was a SUV rollover crisis, that 10, 15 years ago versus, for example, Toyota going through the biggest recall ever, 2010, 11, and still 2 more of them last year, but also being #1 in vehicle sales and winning Kelley Blue Book Resale Value Award, etc. It seems like the OEMs are more able to deal with this and to see it as kind of an indication in a process and not necessarily a crisis that's going to take that off the market. Do you guys see anything different from today, the way that an engineering design team deals with this than 10, 20 years ago? Or the way that NHTSA even responds to it?
Oh, let me give you some history, if I might. I was involved in a recall, although a very small one, back in the 90s with the Ford EcoStar, which used sodium sulfur batteries. And they were an event where basically a fireman just stood around and watched it burn because there was nothing they could do about it. But we learned on the fly, along with Ford Motor Company, and I was with AABC at the time, what it meant to handle a recall with this new kind of product. And it was fairly painful at the time, but I sense the same thing, that it's fairly regimented now. You know, people's roles are well established. I still wouldn't want to go through it, but nevertheless, it's a good, robust process now.
Mm-hmm. Okay. Well, I was going to ask you a little bit about what we were just talking about, battery degradation questions, and the issue of temperature, thermal issues. Has been there for the Nissan Leaf, for everyone actually. That's the most obvious example in the past year. Kevin, we were talking a little bit about what you're seeing there right now and how that goes into your design. And also, I've always wondered, does it matter where you're selling those cars? If you know, for example, in California, there already are certain regulatory standards that go back to catalytic converters in the 70s, but the automakers got used to doing different standards for different markets. Is that an issue with thermal for battery life?
Okay, yeah, good question. So to take the first part on, you know, as you mentioned on some of the stories, you know, about the Nissan Leaf, you know, I won't comment on whether it was right, wrong, or indifferent, but just the impacts of temperature on battery life, and then how that relates to the design and then testing for that. So as we all know, the hotter the battery runs, the less the life is. And that'll impacts both your calendar life as well as your cycling life, your driving conditions. So from a design point of view, you know, we'll start to divide up the battery life equation into, you know, your storage life, which is basically your overnight wire charging condition, you know, in a PHEV, versus your drive cycle. And then what you usually start off with is your initial system simulations for how your vehicle is going to, you know, perform in its application over usually a typical drive cycle. And the way that, you know, what we wanted to highlight is how we would integrate, you know, lab testing with vehicle testing and wrap that into, you know, a vehicle life and battery life equation for that. So you'd start off in an early, you know, proof of concept stage in your lab with the battery pack in your lab, and you'd be running it on your simulated drive cycle, and then you'd look at the battery for two key temperature conditions. One is what is the average temperature of the battery, and the other is a delta temperature across the battery, because both will impact your life dramatically. And one rule of thumb is 10 degrees C per half-life, but I think each chemistry will have a little different flavor towards that, but that's usually a good rule of thumb to use for that. But you start off in the lab, you identify those conditions, you make sure your system is controllable. You know, so that's the one thing, you make sure your average temperature is controllable. You don't have an uncontrolled system where it just keeps going and doesn't achieve steady state. And then you want to make sure your steady state is at a point to where you can achieve, you know, your 8 or 10 year design goal. So, you know, a lot of times you're looking in the, you know, 30 degree C range, you know, give or take, depending on, you know, the chemistry and the application, of course. But you'll be somewhere in that ballpark often. And then once you've gotten your lab results, then once you get on vehicle, you try to repeat the same testing and see if you get the same results. What we often find, and, you know, maybe sometimes you see that in some of the articles, is that, you know, the actual application in vehicle is different than what you got in your lab. Or in your lab, you can maintain a nice even temperature, maybe 28 degrees C, no delta. Then you get it into a vehicle, and now all of a sudden you've got this radiant heat coming off of the road, which makes the bottom of your, you know, if it's an undermount pack, it'll make the bottom of your pack hotter than the top. Or sometimes the front of your pack is going to be hotter than the back because you've got an engine, and that's blowing a lot of heat out back on you. Or there's a lot of different conditions once you get in vehicle that could impact you. So you basically have to do all that testing again that you did in the lab, do it in vehicle, and make sure your results match up. And if not, you have to keep iterating until you can get them to that same point. And then for the part about does geographic location impact life, and yeah, unfortunately it often will, because that gets into, I mean, each situation will be a little bit different, but that can impact what the average temperature is of the battery during storage. Although garages will be somewhat independent, they won't reach the extremes of the ambient, but they'll be affected by that. So a customer in Michigan, their garage is generally going to be a lower average temperature than somebody in Southern California or in Phoenix. Will be much hotter. So as we're working through our life equations, we have to design the battery for the hot the hot climate, for a Phoenix climate, and usually for your worst case driver for that.
Maybe you could extend that argument a little bit. The key word that you had, Kevin, was application, and use another one, application relevance. It extends over into the abuse testing, because we do a lot of tests, as do most test houses, that tend to try and abuse a battery the way that we think it would be abused, and the way that several standards, SAE and a few others, IEC and so forth, have described. But there's still a missing link there to some degree for some of these tests, and that is, how real is it? And that's a big challenge for everyone involved, the OEM, the test house, the cell manufacturer, the component people and so forth. How real is it what we are doing? Does it apply to the customer, who can be anywhere, anytime, any temperature? He can abuse the car any way he wishes, rental cars, for example. And so you've got to make that link, and I think we're in the midst of that process at this point.
Yeah, and to add to that some of the complexity for a plug-in hybrid, for these applications, what we typically look at is if you take a 3x3 matrix where you have your 10th, 50th, and 90th percentile drivers, so your drive conditions will range from highway driving on one extreme, city driving on the other extreme, and suburban type drive as the middle of the road. So if you're certain applications, you'll just look at those three. But being a plug-in hybrid, we have to put that in a matrix. So you now have 9 use conditions, because along the other axes, you have to put your charging frequency. So is a person a 10th percentile, 50th percentile, or 90th percentile charger? And what you get is you get 9 different use conditions, which are dramatically different. Because your frequent charger, he's going to be all deep state of charge swings or deep DOD swings, which is real aggressive on the battery. Your hybrid drivers, so the people who decide they don't want to plug in as much or they get bored with it, they're going to drive more as a hybrid vehicle, which for lithium is going to be a very shallow cycle, and it'll be a lot lower amp hour throughput. So we have a very dramatic difference for that, where we have 9 different drive conditions, and then you have to apply that, back to your earlier question, to the different climates of what do those 9 conditions look like for a Detroit-based driver versus a Phoenix-based driver versus someone in Minnesota. So you quickly get into you can easily get up to 27 different use conditions that you're trying to evaluate, and design your life towards.
Yeah, I think the other thing to keep in mind is that a lot of these things, particularly with life, aren't exactly a surprise. I mean, it shouldn't surprise anyone that the average temperature in the southwestern United States is much greater than it is in the northern Midwest. So that information is available and can be integrated into the design. And our approach, very similar to what Kevin's described, is to look at variations in usage as well as variations in climate, and then design a battery system that meets customer expectation under the most severe conditions. So in a lot of ways, that means that you end up with, in the more benign temperature environments, you end up with a battery system that's actually got more capability than is sort of the minimum necessary. But in order to make sure that regardless of where that customer uses that vehicle, or how often they charge it, or whether they're one of the folks who's trying to see how many thousands of miles they can drive their Volt without filling the gas tank, all of those different conditions end up being a part of that. I think the other challenge is trying to sort out what's the real percentile usage for a hybrid vehicle and for a plug-in, right? As we begin plug-ins and to get more exposure, it's kind of a new type of usage. where, you know, Volt owners, you know, they take great pride in how, you know, what's their longest, you know, single drive without recharge, and, you know, how many miles have they driven without refilling the gas tank. I mean, there's, you know, unofficial contests among Volt drivers of, you know, who's done the most, and so that kind of, you know, peer pressure kind of activity changes what the assumptions are in terms of what that usage looks like. You know, nobody necessarily anticipated all of those kinds of things going in. So, you know, once again, from our perspective, we have the advantage of being able to pull data from OnStar and begin to monitor real-life usage compared to our modeling assumptions, and begin to try to make that correlation. And we're, you know, we now have enough experience with that we're actually starting to be able to do that, and trying to correlate life models with temperature exposures and usage conditions and so forth. And so, you know, as we begin from our own, I'll say, internal standards perspective of, you know, how do we model life and so forth, we started at a particular spot, but then are continuing to try to monitor that and learn as we proceed to what the better usage, or a more representative usage profile is for the drivers of those kinds of vehicles.
Similarly, you know, when we are asked to do abuse tests on different batteries from different customers, we typically do it on new product or slightly used. And in the case of transport, UN 38.3 tests, you know, they have maybe 50 cycles on them or so. But we've seen some evidence from the tests that have been done in our China lab in Shenzhen that, you know, that after a full life, the abuse resilience of some of these cells is compromised to some extent. How much is a hard number to put your finger on, but that's another dimension that we've yet to broach in the kind of people that we're talking to. Might be a little different for the established manufacturers, but there simply isn't a lot of product out there that's old enough to measure this on. So that's another TBD exercise, I think.
When I look at cars today, there's a few things that are very different. One of them, there's a lot more consumer electronics right now tapping into the battery, from infotainment, navigation, regenerative braking, which actually can produce energy, but that's part of it. How does that affect, when you're looking at all of this, when you're looking at a Volt, or, you know, a Fisker, anything that you're looking at for the next few years? How much is the battery responsible for, and how does this affect its capacity and durability, if at all?
Well, I guess, you know, there's sort of two different categories of things. I think a lot of the infotainment functionality and a lot more of the electrical functionality, you know, that provides a bit more energy usage, but compared to propelling the vehicle down the road, it's probably not something that's a dramatic change. Our view there is that the biggest advantage there is the ability to interface more with the customer, to communicate more potentially about the state of the battery, to gather more information about how the customer might be using the battery. So from a involvement of infotainment systems, from that perspective, you know, we look at it from there. Regenerative braking and those kinds of things, there are actually a set of standard drive cycle conditions that go through particular acceleration, deceleration, stop events where, you know, the regenerative braking is integrated into that. And there's a variety of those, some of which are regulated, you know, some of which are manufacturer specific, that are intended to try to represent customer usage, whether they're a city driver or a country driver, as well. So from that perspective, it's integrated in as a part of that drive cycle and usage condition as we try to assess life and you know, what are the usage conditions from a safety perspective as well.
Yeah, I think it's one of those items that It has to be addressed and looked at because the 12-volt loads are definitely a lot higher, on our cars now than they were, 10, 20 years ago. And if you don't do the 12-volt load shedding or power management correctly, it can have an impact on your MPGE, and some of your functions. It's not one of the primary drivers to your efficiency, but it can have an impact on your efficiency. So it is something that you have to look at early on in the development stages to make sure that you've got your 12-volt management. It's basically a solvable problem as long as you put the time into it and get that worked out, so that doesn't have an impact on your or have too much of an impact on your overall range and your overall vehicle efficiency.
Great. I wanted to ask Keith Wilson some questions definitely about standards. This is kind of one of the main focus we're getting to here as well for this whole conference. I know when you're looking at a couple of, we have a couple of things came up. One was certainly about standards for battery abuse. There's also the issue all of you could speak to a little bit later, and that's charging stations, charging infrastructure, and we've had some debate about, where's SAE stand versus CHAdeMO and Europe, et cetera. So let's talk a little bit about battery abuse standards and where that is today.
A number of activities, and when we think about battery safety, it covers a wide spectrum. Everything from transporting a battery, secondary life of batteries, safe handling. Galen's presentation this morning, talked about the need for standards post-incident when there's damage to a battery or a battery system. And we have a large group, actually over 500 representatives that are working together under the umbrella of a battery steering system committee that Bob Gallion chairs. 19 subcommittees working on these standards, everything from secondary use, battery safety, packaging, connectors and connection guidelines, truck and bus batteries, and we get into large capacities there, capacitive energy devices, because we're now seeing additional devices that are storing energy on our vehicles. Battery transportation, fuel gauging, a lot of standards have been developed relative to how do you compare a battery system's output or characteristics of one battery to another. When we think about new technologies when they come out, one of the first needs and standards is, take a look at lightweight materials right now. For instance, how do you compare one material versus another material without some type of standard that allows you to rate the output or the strength or the characteristics of that material? And that's the same thing that has happened here in the battery world. And so a lot of the work that went, I guess, early on was in sort of gauging and measuring energy and outputs there. This work of these individuals, and many of which are sitting here in this group, represent over about 200 different companies. So probably the largest consortium of battery experts in the world working together to tackle some of these issues. They have published about 17 standards that are currently on the books at SAE, along with 10 new standards that are in development right now. So a lot of good work that's going on there. And surely SAE isn't the only standards development organization working on battery standards. We know that there's activities, UL, for instance, is looking at cell level standards. They have lots of experience with testing on a component level and consumer electronics that they can lend into the larger battery packs in automobiles. We've got European community working on proposed standards there. Michael Austin mentioned today in his presentation, there's a flame resistance standard in China that is a 2.5-hour duration. We don't have a standard like that here in the US, so the need is definitely there. There's actually a number of activities that are going on besides the standard development organizations such as SAE and the collaborative effort of members working on standards, but there's also projects, and John Whitefoot from NHTSA today gave a presentation on, I think there was 8 different projects where they're doing basically research, and SAE is involved in 3 of those projects. So managing those projects and helping to advance the technology is another method. And out of that will come more standards as we learn more and more. One of the activities that we're working on that John talked about today was to develop industry standards to address lithium-ion battery safety under a contract with NHTSA. And DOT funded through NHTSA. It's a 2-year project. It looks like it's going to be extended. And the intent of the project is to develop the industry standards to help produce or assure safe vehicles in the marketplace. And this is a sort of a wide spectrum of research that's going on that covers everything from battery abuse to all the potential conditions that we may see in the vehicles in the stream of commerce. So this particular project, we started out working with 5 OEMs together on. We had GM, Honda, and Toyota, Nissan, and Daimler working together under the SAE umbrella to help develop those standards. We're now broadening the scope and actually going to provide an opportunity for input from other organizations and individuals into this process to help us to develop these standards. So research foundations and institutes, universities, battery consultants that we'll bring into the fold here and continue to develop these standards. So some of the standards that are being developed in this program range from vibration, thermal shock, overcharge, over discharge, over temp, under temp, flame resistance. We are looking at a couple tests in flame resistance, water intrusion, that we talked about earlier, and then, of course, in each one of these, then what's appropriate? What parameters are appropriate so that these standards are robust and can help to ensure good products in the marketplace? But do you develop test standards that that are very aggressive in nature? Take for instance exposure to say a thermal shock condition. There's not too many real world conditions. We can think about the vehicle that may be in California in a very hot environment and then be pulled into a air-conditioned garage. Well, the temperature swing there is pretty large, but it's not dramatic, if you will. And so you think about, is there really that many real-world conditions? I guess the one that I can think about that's probably the most dramatic is having a vehicle that's out in very cold sub-zero weather and then pull it into a paint booth and work on it in a paint booth atmosphere with high-intensity lamps and a large amount of heat. How many times is a vehicle going to see that type of environment? Probably not very many. So, you struggle with how many cycles would you run or develop in your test to simulate that, or to simulate something more aggressive than that. And so those are some of the struggles we're having. This is also a collaborative effort, and just like the SAE standards work, these projects are also collaborative. The other 2 projects that we're engaged in, one is stranded energy. And, John touched a little bit on it today, that NHTSA has a project with Argonne National Lab, and Sandia National Lab's involved in that one, also in SAE. And so, the real need there for the first responder, second responder community, and to Galen's point that he made, there's sometimes that you want to pull the energy out of a battery system where it's safe to do so, and there's other times that you don't. Well, how do you assess when it is and when it isn't? And so it's very complex in nature. So doing that research is absolutely instrumental to give us more answers and indications. So
I think one of the challenges around standards, and certainly SAE has been very instrumental facilitating, standards within the battery safety area in particular, but batteries and obviously lots of other things. One of the challenges as I led an effort to create the battery safety standard is the ability to actually have data to bring to bear on the discussion, and that without data, there's as many opinions as there are participants. In some cases, maybe even more opinions than there are participants about what the right thing to do is, and so I think that as we gain more field experience, as some of this research work is completed and published and so forth, I think that we're going to be in a better position to be able to create meaningful standards out of that. I mean, that I think is really the challenge. When you're faced with no data, you kind of get what everybody is willing to agree to, which maybe isn't as much as is necessary. But once the data exists, as objective engineers, which is what we're, most of us are trained for that. The answer is more clear and less controversial, and so I think that's one of the real opportunities that we have here as we go forward through the next few years, as we gain more understanding in terms of field experience. More research is done, either sponsored by NHTSA or work through the OEMs and other places. And I think it's really important that data isn't strictly internal, isn't just internal data that can't be shared. And when we reach the point of being able to do that, I think the standards activity will take another dramatic step forward as far as how to create those standards for batteries.
Galen makes a good point in that, we're dealing in a competitive environment. At the same time, we need to share the information that we generate and produce here. We're involving organizations such as TÜV SÜD, Southwest Research Institute, Sandia National Laboratory, OEMs, and others. And I mentioned that we're broadening the scope of this to include additional subject matter experts into this program, and it does rely on the fact that we need to share that information. And the OEMs have been very forthcoming, I guess, to get involved in this project. At the same time, they know that their products are being exposed, and some of their design information may get exposed. So it is somewhat risky. At the same time, they know that for the betterment of the technology, it makes sense to work together on this.
I think we're seeing a lot of work in the standards, especially on the abuse standards, as we've been talking about. Going back to the first question about nickel metal hydride, when we're designing a lot of our systems for that, is just a couple of standards. 2464 was one of the key ones I know we used when we developed that. And now, in Dan Dowdy's presentation from the other day, he has a matrix of all the different standards that address battery safety and battery abuse, and then had a matrix of which similar requirements were covered and which ones. So you can see there's a lot of good work on there, which is great for the industry. And then I think it would be helpful for some of us if we maybe start to coalesce them into more of a unity standard.
I'll bring an interesting side note to this, is that you can see how much effort it takes to put these standards in place and to verify that they indeed are doing the kind of test work that we want them to do. But we in our work with many, or at least a few companies, can see that, in the haste to try and get all this done, they put, in some cases, pack samples and so forth in our test lab where we know they're going to fail before you even put them on the test. For example, an immersion test where you can see inside the pack, a vibe test where parts are loose already, shock test, same sort of thing. Most companies with a strong, good process for handling a design verification program don't have this happen to them in most cases. But when you're driven by the investment community, which is probably driven by the media and who are trying to satisfy the public, who want breakthroughs, cutting-edge technology developments, and so forth, there's a lot of pressure inside some of the smaller companies to really rush this through and do the test regardless of whether it's going to fail or pass. So often we find ourselves in the position of saying, you know, take a look again, see if you really want to do this test. Maybe there's some homework you should do first.
I wanted to ask you too about what you're looking at the charging infrastructure, which is new, very different from the way it was in California in the 1990s. We're seeing, I know a lot of people have been using 110-volt chargers out of their garage, and even early Leaf and Bolt owners, and now a lot more of them have done level 2 charging stations. A lot of workplaces are putting them in, public facilities, condos. There's also the fast charger issue, which is still very, very new. There's not many of them out there, but that's a good one for a conversation. Where is SAE looking at all of this right now?
You know, and I'm sure you're all aware of the fact that there has been some recent developments in that the J1772 combo connector has been released for publication. So this is an AC/DC level 1, level 2 connector, and you know, again, another collaborative effort of about 190 participants and members working together. And you know, the OEMs and the EVSC manufacturers, along with suppliers, worked together and steered this in the direction of a single combo connector that they could be used for multi-purposes. So it covers that 110-volt plug in the garage to the 220-volt box that somebody's going to put into their garage or in a multiple unit dwelling. And then the fast charge, the DC fast charge, along with the fact that, you know, it has some future-proof concepts in it, and that it allows for reverse power flow. So, you know, where that goes down the road, we don't know, but having that capability to be able to feed power back into the grid from a stored energy device through that connector. But here's something else that we're actually, you know, involved in here, and this is part of that stranded energy. Is it possible that that connector or something similar to it could also be used from a reverse power standpoint to help a first or second responder to pull energy out of a pack when it makes sense to do that? But going back to the charging community, so this connector was also harmonized with the IEC connector, so the similar configuration of a combo connector. Although I heard yesterday it was announced that the European community has decided that they're going to go with a Menake's Type 2 connector as their standard. So we had hoped for some international harmonization there in that, as an OEM, fitting your vehicle for whether it's the IEC combo connector or the J1772 combo connector requires the same system. And since then it becomes a matter of replacing the connector body itself or the receptacle body itself in the vehicle. Apparently that's not going to happen, so we still have a lot of variation out there in the charging world. We have CHAdeMO chargers that are been implemented across the U.S. We have talked to, and in fact are involved with, a number of EVSC manufacturers that say those units are easily adaptable to have both connectors, or either connector, CHAdeMO or 1772. But you know, another aspect of this whole thing is interoperability. And we've got this variability in this hardware. And if you look at like a Tesla vehicle, they've got a whole kit, right, of these different adapters to allow them to connect to any different type of device. But what makes sure that a Chevy Volt is going to work with an equality device, charging unit, or a Nissan Leaf is going to work with some other EVSC manufacturer's device? There's really nothing in place. Here's another, you know, lack of industry standards there currently in place that assures interoperability. So we have a project we're working on under, actually DOE is funding this, and Equality is the primary contractor, but it's a round-robin test series. So we test all the vehicles that are in the marketplace, are going to be in the marketplace in the next 2 years, with all the EVSCs that are going to be in the marketplace, and we then develop some standards that everybody builds to. We build vehicles to, and we build charging units to. And so that's actually, that testing will begin beginning in April timeframe. And Argonne National Lab is actually involved in some of the testing now. So that will help the interoperability aspect, but the variability of chargers and plugs is an international issue. And 1772 helps to condense the number of adapters needed and to allow one charger in 3 different power modes. And so that's been a good step there. The other standards that are associated with that connector are use cases, message sets, and the technical information. So you want your vehicles to be able to talk to the grid. You want to be able to transfer billing information. You want to transfer usage information. You want to be able to schedule charging during off-peak load times and reduce rate times. And the ability to do that comes in this communication that is being developed. So the communication standards, there's actually a set of 3, 2836, which basically provides the use cases. 2847, which is the message sets and what information is going to be transferred between the vehicle and the grid. And 2931, which is the technical information. So what are the bandwidths and the frequencies of that information that's being transferred? And those standards have been published, and they're continually being updated and to help that future capability of communicating between the vehicle and the grid.
Yes, I just want to echo something you touched on briefly at the beginning, is this idea of international harmonization. You know, the unfortunate decisions around the fast charging connectors is just, you know, one example where standards as well as regulations globally are not harmonized. You know, and from a vehicle manufacturer perspective, from a battery manufacturer perspective, that lack of harmonization translates directly into more effort from a development perspective, and more cost in terms of variations in product potentially, and so forth. And you know, we strongly believe that, you know, international harmonization to the maximum extent possible is really important. And there are some efforts in some areas around electric vehicle safety. There's an activity underway sponsored by or co-sponsored by NHTSA globally for an electric vehicle standard. You know, that we're certainly supportive of the concept of a globally common kind of a device, because, you know, no more is there just product that's primarily one market, at least for General Motors. And so that becomes really important. And there are actually some other efforts. ANSI is the United States, I'll say, primary standards organization, is actually sponsoring a meeting here. I think it's in a couple of weeks, right? With the VDA and with some other international organizations to at least discuss this issue and begin to try to identify where are those variations, where can we in fact become, you know, where are the opportunities for commonality, and, you know, where are the real gaps. And so, you know, I think that's the right thing to do, because there are a few things that are different based on market, some, you know, things like usage and, you know, sort of as-built infrastructure that's already there, and some cultural things. But by and large, most of these kinds of standards don't necessarily need to be unique by market. They're often unique now just because they were developed by 2 different groups, and there's no fundamental reason why they need to be common. So we're certainly hopeful to be able to move things in a direction of globally common when that opportunity presents itself.
Yeah, it's good to see that, we are getting DIN, ISO, ANSI, SAE, IEEE, actually meeting together and trying to work towards the goal of common standards here for electric vehicles.
One quick question I had when I was thinking about, is there any concern in terms of DC fast chargers on battery durability compared to a level of 240 volt charger? Do you have experience with that with lithium ion batteries? Are you confident that that's not or is not going to be a durability issue?
I'll defer to the car guys.
It's definitely something that needs to be looked at to verify that it isn't an issue. So lithium, yes, certain chemistries or certain cells might have issues with fast charging. Sometimes there's some plating issues that need to be looked at, as well as some other issues with the chemistry. So I believe it is possible to do fast charging. It's just one, you have to make sure the life tests are run, and you can verify that there isn't any additional life degradation due to the fast charging as compared to a slower charging.
Yeah, fast charging isn't something as simple as putting on the new connector and running a couple wires to the front of the battery. I mean, making sure the battery is capable of receiving that charge, and the overall system design, making sure that there is no issue, right? So your question about will there be an issue, the answer is by the time it gets to the consumer, we don't believe there will be. But the development effort to try to make sure that's the case, certainly there's work to be done there to make sure of that.
Okay, thanks. So I think at this point we were, our schedule is for networking and one-on-one Q&A opportunities. So for those of you who would like to come and speak to our panel, thanks very much for doing this. This is good information. Appreciate it.
Thank you.
Hi, I'm Chris Rural from Charge Magazine. It seems like there's some obvious safety standard gaps with regard to kind of crash events or hurricanes and stuff like that, but are there any major standard gaps that you guys have identified with regard to regular use? Like, are there no, is it vibration, or maybe kind of what is the most pressing kind of regular use standard? Is it like fast charging or a regular duty cycle, like with the case with the Volt drivers?
I would say that the biggest gap is definitely in abuse versus, say, standard driving. I think that the standards that are in place cover at least a level. Well, we look at the product that's out there in the field, and Galen touched on this morning. The failures are at such a low rate, and yes, we've had some incidences, but those have been very unique type incidences. So the standards, I think, are helping to put into the marketplace a certain level that in standard use is adequate, whereas in abuse situations, and how far do you take the development standards to address abuse situations? I mean, I think we've all agreed that we don't want to develop a standard that simulates Hurricane Sandy. At the same time, water intrusion is something that we need to address at some level. Flame exposure is another one. It's the potential's there, but do we need to barbecue a battery for 2.5 hours? That's the question. That still needs to be developed or handled there. So I think basically that's the concentration is the abuse arena.
Thank you. Anybody else?
I have a couple questions. One is, do you really think harmonization of standards is going to go forward? Because I don't see the motivation of the standards-making agencies as being aligned with the needs that the auto industry have. I mean, as a matter of fact, I think their motivation is divergent. And although it would be a good outcome, does anybody really think that's going to happen?
I think we're seeing more progress than we've seen before, especially in electric vehicles. So, for instance, we have memorandums of understanding with IEEE, ISO, and DIN that we've never had before, and those are in specific technologies. Electric vehicle is one of those technologies. So there's progress there. When I look at the fact that, you know, the standards are developed as a collaborative effort, and it's sort of the industry that's moving the standard in a particular direction. And to Galen's point earlier, you know, they're developing global products. They need to have standards developed such that they can build a product for the market no matter where they're going to sell it. And so it's in their best interest. We're finding that a lot of these committees are having their members involved in, say, an IEC committee working on chargers, and also the SAE committee, and the documents end up getting shared. And so the direction seems to be better that these two organizations go in similar directions there. And it's from the community driving that.
I hope you're right.
Yeah.
I guess I would say I think there's hope there. The other place where we're fairly optimistic is with the development of global technical regulation around electric vehicle safety, which is under the UN auspices of the UN, and it's a global regulatory body kind of a thing. And with the United States in the ECE co-sponsoring, and I believe China is serving as a significant role in that as well. You know, we think that there's real significant potential there that's going to set us up with a globally common regulation. So in addition to sort of the optimism I think that exists within the standards organization, we think that from a regulation perspective, there's certainly an opportunity to make that happen there as well. So. I guess we'll all see in a couple of years, right?
Yeah, I think that's going to have a big influence. You know, NHTSA has the lead as the U.S. entity there. So when you look at the research that they're doing in battery technology that John talked about earlier today, you know, that's all going into their intellectual property to help develop the standards there and the proposals for standards for the global technical regulation.
Another question is looking at gaps in safety testing or in areas that there's a lot of work on. I hear and I see a lot of development on an internal short circuit test. I have my own opinion, but I'd like to hear what your opinion is on whether that should go forward, whether it's, you know, what do we, as an industry, what should we be doing about that?
Well, let me try and answer that. We've done an awful lot of simulated short circuit work, both through you know, indirect methods, overcharge, penetration. We've done penetration with standard steel nails, different sizes, different configurations, ceramic nails, nickel-tipped ceramic nails, some plastic nails, all trying to feel or to feed the wishes of our customers to try and characterize what happens inside a cell when you get what we don't call it short circuit, we call it an unintended current path. And it's a subtle thing.
Is this like rapid expansion?
I suppose
it's a euphemism.
No, it's.
Oh, sorry.
It's very similar to RESS when you mean battery. But the point of this is, it's all research to come up with what is the mechanism. How do things happen? Do they happen because you've got a conductor sliding through it from a defect, or does it happen because you've got anodes and cathodes touching each other, regardless of whether there's something there or not? So yeah, the answer is it should go forward. Until we completely understand how things go wrong, it should happen.
Any other questions? I think the panel will be around if you got one-on-one questions for them. We have the room for another half hour or so, is that right? So thank you all for coming. We really appreciate it.
Okay.